also a lecturer here at UNSW. So I'm a functional morphologist. My area of expertise is really in trying to understand what these extinct organisms are doing within their environment, what they're feeding on, how they're moving, how they're functioning. And today I'm going to be talking to you about a project that's still ongoing, looking at the evolution of these strange ridges of enamel on marine predator teeth. So this project is about apicobasal ridges. So these are ridges of enamel that run on the long axis of teeth. They're different from things we call McCurry in that they occur in greater number and across kind of patches on the tooth surface. Sometimes they're all the way around the teeth, but other times they're just located on one side of the tooth. These have been referred to as striations, fluted teeth, but today I'm just going to be calling them ridges. The interesting thing is that they've evolved in a wide number of different groups. So that got me interested in trying to figure out exactly what these striations mean. So they're often used as a taxonomic tool to identify teeth to a higher level, but no one's really looked into high level of detail about what they're for. So there's a few different possibilities about what these ridges could be doing. So one is that they can improve puncture efficiency. So maybe animals are using these teeth and the ridges as kind of accessionary cutting edges to better allow them to puncture certain types of prey. In that way, they might perform similar to a bodkin head arrow tip that we use to puncture certain types of armor. Almost completely opposite, they could actually be to remove the teeth more efficiently from a prey item once they've been punctured. So in this way, they might function similar to a grating-edged knife. So some knives that humans have designed are used to cut into certain types of things that we're trying to cut, and these ridges break the suction so that the knife can actually be removed easier. They could also be to help grip on certain types of prey. So maybe slippery prey like fish and squid require a bit more grip to hang on to, and in that way they might function similar to fluted nails that actually better allow things to hang in compliant materials. Or they could be to strengthen the teeth. And in this way, they could function similar to these ridges that were placed onto bayonets to increase their strength in bending. So the aims of this project were really the first steps of this. So to clarify exactly which species these ridges have evolved in, and to compare the morphology among the different individuals that have these ridges. So to do this, I went to a wide variety of museums. As I was traveling around for other projects, I looked at a lot of teeth, and I noted, in which species have these ridges, which species don't have these ridges. I then took a subsample of these teeth that I looked at, and I CT scanned them in this machine. It's a micro CT scanner. It was custom built for military functions in the US, so it can take things up to the size of a whale head, but scan them at micro CT resolution. And from these CT scans, I can measure a lot of characteristics about the external shape of the teeth. So to do this analysis, I broke it down into 3 main layers within the tooth. I can measure things like the height of the ridges, the width of the ridges, exactly how much of the surface the ridges are contained on, and I can also look at the internal morphology. So I can measure the thickness of enamel in these teeth. So the first finding was that these traits are extremely common in aquatic feeding species and extremely rare in terrestrial feeding species. So they've evolved in a really wide range of taxa, everything from early whales, some species of seals, at least 3 different lineages of aquatic feeding snakes, mosasaurs, pliosaurs, ichthyosaurs, some really weird aquatic feeding animals, as well as animals that live on land but feed in the aquatic environment, like spinosauric dinosaurs. So this trait really does seem to be linked to feeding in the aquatic environment. Now, there are some differences in the external morphology of these ridges. In some species, they kind of interweave, creating more of a interweaving shape. In some species, they're slightly higher. In some, they're slightly more pronounced. Whereas in others, they're slightly more rounded. But overall, as you can see, they're quite similar in their morphology. So these ridges are really quite similar among these different species that are each evolving them independently. So one thing I should note at this stage is that not all aquatic feeding species have these ridges though. So species like modern dolphins have smooth teeth. So it doesn't seem to be something that's universal for feeding in water, but it seems to be something that's useful for some aquatic feeding species. I looked at the scaling relationships of these ridges. So the number of ridges doesn't change as you increase size of teeth, but the height and width, so the size of the ridges themselves do. So it seems like some of my images have actually left. Quickly see if I can leave them up. Oh, sorry, there's some technical issues. But one interesting thing is the internal morphology of these teeth. So the characteristics inside the teeth are completely different. So in some species, they're infolding the enamel to produce the ridges on the outside, whereas in other cases, they're just locally thickening the enamel to produce it. So I anticipate this is actually due to completely different genetic mechanisms. So the organisms have evolved completely different ways to generate these ridges on the outside of the teeth. So it really is an example of independent evolution of the trait. So the conclusions of this talk are really that apicobasal ridges are an aquatic trait. And the second is that they don't seem to be linked to the strength of the teeth. So if we look at characteristics that we normally associate with feeding on hard prey or large prey, they're robust teeth and they're thick enough. In this case, we didn't find that. So we found that ridges evolve in a wide range of tooth morphotypes, including slender teeth that are not associated with feeding on hard prey, and that it's not linked to thick enamel at all. So we can rule out that one idea about what these ridges do and move on to testing the other ideas. So from here, I hope to 3D print teeth with and without these ridges and actually measure what they can do puncturing into different types of prey. Okay. Sorry about the technical difficulties. Has anyone got any questions?
Yeah, that's very interesting. The question is, where you got the ridges on these teeth? Is it by any chance on the basis of the teeth that would encounter opposing teeth in the other jaw?
So no. So there are some examples of that in the aquatic environment, but most of these teeth are simple and conical and don't interact with the other teeth themselves. The interesting thing is they do evolve on the surface of teeth that interact with the prey. So if teeth are recurved, and so if you think if they're puncturing into a certain prey item with a recurved shape, there's this kind of dead space on the other side of the tooth that doesn't actually end up touching the prey item at all. And in those cases, the part that doesn't touch the prey item is often smooth without the ridges. So we think it's really important when it's interacting with the prey itself.
Because of course you do get ridges, not necessarily as precisely linear as that in a lot of mammals. And there, these are definitely sharpened by tooth-tooth interactions, resulting in increased sharpness of the actual edges of the regions, the sides of the ridges, and they become assisting blades in the cutting of the material that's being created.
Yeah,
So I can see if they're not actually including, and that's true for all of the groups that you're looking at. You don't get any actual dental occlusion.
So
I thought some crocodiles.
So you do get abrasion between teeth, but in many ways these teeth are acting far more simplistically than a lot of the money teeth that you're talking about. So they're simple, they're conical. In most cases, they're not even touching the other teeth. In some cases, they are, but they're really just kind of abrading away at the surface and not interlocking as you would expect in kind of terrestrial mountain teeth. I think that's partly because the environment doesn't really allow for a lot of the things you can do in a terrestrial environment. So things like predators on land often use the gravity or their arms to manipulate prey as they're feeding on them, whereas in the aquatic environment, that's really limited. So the limbs are adapted for locomotion and no longer useful for manipulating prey within the mouth. And if you think about trying to grab or pull at a prey item to tear it apart, it's not really possible when you're buoyant in the water. So these animals end up doing things in quite a different way. They'll move to the surface and they'll shake prey to try and dismember them, or they'll try and swallow them whole. So in many ways, they function completely differently to terrestrial mammals.
Well, why wouldn't it be an assistantly in holding on to slippery food? Because when one of these animals bites a fish, the fish is going to try to get away. And if the teeth are all smooth, theoretically, it pull itself off those teeth. The ridges, vertical ridges, they might resist that ability of the animal to escape past those teeth.
Yeah, it's definitely possible. So I should clarify, I haven't ruled out exactly which of the other three functions is possible. So they could be to grip prey items, they could be to increase puncture efficiency, or they could be to remove the teeth more efficiently. The only one I've ruled out at this stage is they don't seem to be associated with feeding on hard or large prey.